like this thing's on? Okay, so these are all my clothes, but I am not Frank Pfenning, if you hadn't noticed. So Frank is out of town at his son's PhD defense. And so he asked me to give this invited lecture, and so I'm giving going to try to cover a couple of topics. I may not get to all of this, but that are near and dear to my heart, which is we've been talking about a particular substructural logic, linear logic, for most of this semester. The midterm gave you a taste of what some other substructural logics might be, and so I'm going to return to that, and then we're going to talk about another substructural logic that wasn't on the midterm, called ordered logic. The way I'm going to motivate this is by, and I forgot to write the date down, starting with a presentation of sequent calculus. It's really the first presentation of a sequent calculus by Gensen that was used to prove the consistency of the logic that he was dealing with a cut elimination argument. If you ever have a chance to read this paper, I'd recommend it because it's eerily familiar. The notation that he uses is really very much like the ones we use today. There are a couple of minor differences, though. One of the differences is, well, if I just gave you the rule for, Gensen's system is for regular old persistent logic, the logic that we're used to, not for linear logic. But if I gave you the rule for, the left rule for implication, because it is a sequent calculus, you would think that I was defining linear logic. So if I have one context, according to Gensen's system, that I can prove AN, and I have another context that is extended with B, from which I can prove C, then using the combination of the two, I can prove I can use A implies B if I can prove A to get a B. So I've actually combined the two contexts. The rate rule, by the way, is the one that we're used to. Gamma gives me A implies B if by extending the context with A, I can derive B. And similarly, this isn't exactly the rule that Gensen uses, but you can write down rules for implication that look like the ones that we're used to from the sequent calculus. So for instance, you've got gamma, if gamma and delta give me A and B, or the way I prove A and B is I use part of my context to prove A, and I use another part of my context to prove B. And then the elimination rules, you should be slightly frightened when I write these elimination rules down, are that if I have an A and B in my context, well, I can just take that down to an A, or I can just take that down to a B. So from the perspective of the linear logic that we've been dealing with, what's terribly wrong with these rules? These essentially allow weakening, or another way of looking at it is they necessitate weakening. Because if I try to prove the completeness of A and B, what's going to happen? If I try to prove that A and B proves A and B, am I going to be able to do that with just the rules I've given you? Okay, what? Because, well, I can only apply one of two rules to this, and either it's the A or it's the B, and then I'm not going to have enough evidence to, well, I'm only going to have one thing. It either has to go here or here. I can't prove both. The way that this system, and this is a style of presentation of sequent calculus that is still used by many people today, the way that he dealt with it is that, well, you actually need a way to duplicate this resource. So it's actually you can phrase it in terms of weakening, but the easier way of fixing the problem here, the problem with identity, is in terms of a rule for contraction. Or, sorry, if I have an A in my context says the rule for contraction. So let's call this rule C. then I can get 2 of them. That's reading it from bottom up. A way of reading it from top down is to say that if I have 2 of a thing that I use to prove C, then all I need is 1 of them. If you think about this in terms of the persistent, the replicated resources in the process interpretation, what this is saying is if I have a replicating resource, a bang send, then if I have 2 of them, then I can just take in my process all uses of one of them and rename them to the other one. And so I only need 1 copy of a process that I can use multiple times. And because what Ginson was trying to do with this system was capture persistent logic, not linear logic, this made sense. The rule that you were mentioning was that I need to also say that if I can prove C, then I can prove, then I can add another fact and I can prove C. Okay, so there's actually a third trick that's going on with Ginson's system. And so this is called rule W for weakening, which is that Ginson, at the beginning of his paper, says we always have to start out, what's a context? And he says that a context is just a list of propositions separated by resources. So in fact, if we start trying to prove, if we start trying to use these 2 rules to prove the new identity property, well, we can get A and B, A and B, using weakening. Sorry, contraction, thank you. So you can prove this, but then if we, and then we can maybe apply one of these left rules. I should have called this and left 1 and this and left 2. So A and B, let's make this an A. So this is and left 1. So now if I want to apply and left 2 to this proposition, I can't do it according to the rule I wrote down, according to the way that Ginson defined his sequence. Because while we've always been thinking about our contexts as what are called multisets, just bags of things, he was describing them as literally sequences. And so in order to switch the position of propositions in his list, he needed a rule that said if I have 2 things that live somewhere in the middle, then I can switch place. Now, in practice, this rule is awful to work with because you can really switch the position of any propositions in the context with this rule, but you have to do it slowly, sort of by bubble sorting them along. But for this example, it's not so bad. We can now apply our rule of exchange to A and B, A and B. And now we can apply and left 2. And I need to be slightly taller, but now we can apply and right. And the A goes over there and the B goes over there. And we're done. Just barely. So now we've used both the rule of contraction and the rule of exchange to deal with the identity property. If we were trying to deal with cut, then there would be better examples that would show why we would need the weakening property as well. Those tend to be a little bit associated when we're dealing with persistent logic. OK, so essentially what Ginson's system has is it has a bunch of rules that are way too restrictive from the perspective that we're looking for. But you have these other structural rules that allow you to manipulate the derivations or manipulate the sequence in a way that you get back the system you want. One of the reasons that we don't tend to work this way is because we're interested, as we've seen this semester, in the computational meaning of the cut admissibility proof and the cut elimination rule. And if you actually have a sequent calculus with these rules and this discipline, and you need to prove cut admissibility, well, let's look at what might go wrong. So the statement of cut that we are, one of the statements of cut that we're used to, there are a lot of ways I could phrase this, but let's just go with the obvious one, that if gamma proves A, if, and gamma A proves C, then gamma proves C. So this is cut admissibility for a non-linear logic where I have the same resources in both places. And there are going to be a lot of problems in writing precisely this proof for this modified presentation of logic, but let's look at one of them in particular. So say I've got my last derivation of this is, well, I've just got a derivation of A, but then my second derivation ends with a contraction rule. So A proves C if A proves C. And what I need to show is that proves C. All right, so how can I proceed? Or what might go wrong if I try to proceed in any obvious way here? Right, so, and then I get, so which of the A's would you like me to cut against?
That doesn't matter.
Okay, so let's say,
Then you have the other one there.
Well, you have to, if your exchange is explicit, don't you have to cut against the outer one?
good call. I have to cut against this outer one. So I could exchange them, yeah. Right, so this is part of it. So we're used to, in the way that we've been dealing with cut elimination proofs, a very important property, which is that when we do cut elimination on the structure, we get to exchange things around, and we get to weaken things around, and we get to say that there could be multiple copies of something, but that's just as good as having one. And that doesn't change the structure of the derivation. That doesn't change the shape. And so the normal termination argument for cut elimination is that you haven't changed the shape. It requires that when you call the induction hypothesis, you haven't changed the shape. So that's an argument against what I think was going on here, which was, can we use exchange to cut against this one even if we wanted to? Not that it makes a difference. Well, there are ways to finesse that by basically assigning some score or weight to derivations and saying that the weight or score always goes down, and then you can work that out. But we have a bigger problem, which is that
Is it actually, you have to do that, like assign the weight to that? Because, well, if you could rephrase the rules so that exchange is derivable.
Right. So what I'm talking about is why we usually don't rephrase the rules so that such that exchange is derivable, right? So we've all seen the system throughout the semester where, like, this is a property that we just can take for granted for the persistent context, not for the linear context, and it doesn't change the structure of a derivation. And similarly, this is a property that this actually never really comes up because the copy rule that we're used to in linear logic, let me go ahead and write that over here, essentially has a built-in, sometimes the way that this is described is that the copy rule has a built-in contraction because you are duplicating the A, it's just that you're putting the other one in the linear context. Okay, so the bigger problem with this proof is that after I cut once against either one of the A's, now I have the same thing I started with on the bottom. And if I try to cut again, well, there's no way I'm going to make a termination argument that makes any sense with by AH on, so call this 1, and on D1. Unless a formula gets smaller, unless the principal formula gets smaller, we can't cut against the same thing twice. That's totally not allowed. One way of understanding what's done, this is, and there are lots of different ways, again, to finesse this, but fundamentally the way that you fix this is you say, I can have all the instances of A that I want here, and I'm cutting against all of them at the same time. And so now I can say that the conclusion simply follows by the induction hypothesis on, so this is some number of A's. And this is now one more A. And now I can say that the induction hypothesis follows on this cut against this, because if I can cut against any number of A's, then I can just call the induction hypothesis where I've cut against one more. So again, I'm not giving all the details here, but that's basically a way of saving the cut elimination argument in this system. And it's roughly similar to what Gensen does as well. What Gensen does is actually say you have to cut against all of the A's in the context. They're all gone. And so the way that he writes this is, well, he writes this as a different context. And then he has a notation for saying, delta prime, where delta prime equals delta with all A's removed. So this works if all you're trying to do with the sequent calculus. Oh, yep.
So what goes wrong if you try to do the induction hypothesis thing twice?
Oh, well, I mean,
And if it terminated once, it will terminate again.
But it might be bigger than the original.
right. The question is, so I think that there's a difference between asking about what is yes, the terminate. Well, I think you're right that the termination procedure would still terminate. It's just but there's a question of how do we actually show, like how do we write down, how do we convince ourselves and each other and potentially the machine that's checking our proof that this is a termination ordering. Because we talked earlier in the class about what the termination ordering usually is for cut elimination proofs, which is either the formula gets smaller or the formula stays the same and at least one of these gets smaller. And that's definitely not happening in the thing that I sketched out before. The output of cut elimination may in general be much, much bigger than the things that you put in. And so I'm recalling the induction hypothesis with this and with a potentially much larger form.
Okay.
Right. And so yeah, so maybe there's some really complex cut elimination like termination metric that you could give. But the point is that the termination argument that's sort of the one that we're used to, the right one, does not work anymore.
Okay, because one is much bigger than D and E.
Because one could be much bigger than D and E. Exactly. Right. Okay. Right. So that's just, and so the reason that we don't like, for our purposes, one of the reasons that we don't like this style of presentation of a sequent calculus, the reason that you haven't seen this before, is that this notion of cut elimination doesn't really mesh well with the computational understanding of cut elimination that we've been dealing with so far this semester. That said, it's an interesting way of exploring the structure of logics a little bit, and that's the thing that I wanted to get to next. So in the midterm, you guys saw that it's possible to define, or one of the questions was that it's possible to define an affine modality such that in linear logic, which is a little bit more permissive than linear logic. It's one, and the way that that was defined, if you guys looked at the answer sheet, or the solutions that Frank sent out, I think last Wednesday, was that you have a choice for something that is an ADA, which is that it can either be the A, you can either choose to get the A, or you can choose to get nothing at all. And so the affine modality is one where you don't have to use every resource. So there's another way of describing affine logic, a logic where everything is affine, which is that affine logic is Ginson system with weakening and exchange. Just like all of logic, the persistent logic, the logic that Ginson was trying to formalize, persistent, admitted, weakening, and contraction, and exchange. So the other thing that Frank suggested on the midterm was a modality for a strict logic, where you have to use the resource A at least once, but you could use it more than one time if you wanted to. And the way that he defined that was a tensor bang A. This is one way to talk about strict logic. The other way to talk about strict logic is that it's Ginson system. Strict logic, by the way, is also sometimes called relevant. Is that it's Ginson system with contraction and exchange. So think about why that's the case. If I have a system with just weakening, then if I have something in my context that I want to get rid of, I can just take it away. However, I can't use it more than once because I don't have any way to duplicate resources in this system. If I want a system with if I want a relevant system, then I can't ever ignore something that's been introduced into the context. But if I want to use it multiple times, then I'm perfectly allowed to use it multiple times. And then linear logic which is the system that we've been working with for most of the semester. And I should stress, this is linear logic without exponentials. If I just want to define the core part of linear logic, the part that we dealt with first without exponentials, that's just exchange. Because exchange is what lets me treat these contexts like multisets, that lets me mush stuff around and treat the context just like a bag of stuff instead of like instead of a list of stuff. And that's the property that we want out of linear logic. And so there's another logic that you can get if you try to consider Ginson system, but then you just really try to consider Ginson system. And ordered logic is when you don't have anything at all. So the null set of structural properties gives you something like ordered logic. Well, and these rules are not the right rules for ordered logic because the left rules, as we saw, don't match up with the right rules in a way that makes sense. So let's actually work out what ordered logic is supposed to be. All right. So the sequence that I'm going to use, the sequence that I'm going to use to describe ordered logic at first is going to be, I'm going to describe a context omega, and from here on out, when I write gamma and delta, I'm going to assume that it acts like a multiset, just like we're used to. But when I write omega, this is a context that's going to act like a list. It's going to act like the lists in Ginson's logic, and proves a proposition A. So omega is a list. A has the form, well, let's think about this. We've got some atomic propositions P. That's the starting point. So the rule that we want for P is that if my sequence of propositions includes exactly one atomic proposition, and it's P, then I can prove P. And then another relevant, sorry, wrong word. Another proposition that we want to deal with is ordered conjunction. So let's think about what a proposition for ordered conjunction would be. The introduction rule is going to say that I can prove that this context has the structure of an A followed by a B. So, in linear logic, when we had tensor, we split up our resources, and we said some of the resources have to prove A, some of the resources have to prove B. This is the ordered version of that. This says the left resources have to prove A, and the right resources have to prove B. Oh, sorry. 1, 2. All right. So, any suggestions on what the left rule should look like?
Same as before.
The same as with linear logic?
Yeah.
Okay. So, pattern matching against linear logic I'd get, and I will go ahead and leave space so that I would get this. So that's close. Why is that not quite right?
Because you want to be able to do it on A conjunction B, wherever it is in the context.
Right. We don't have exchange anymore, so we can't just exchange something to the front like we did in Ginson's system. We need to let this happen at any point in the context. All right? So, yeah. Oh.
Does B maybe need to be after the omega r in the top one?
Well, let's do a sanity check, why don't we? What are the sanity checks we usually do?
Prove.
Right. And if we don't want to go all the way to proving soundness and completeness, we just state them and prove the principal cases of cut. So I don't want to go through the whole cut admissibility proof, but let's just do the principal case. So identity is going to be the same as it ever was. A proves A. So in this case, we have a B proves a B. So what do we do first? Yep. So the first thing we do is we compose a left rule. And now we use the right rule. A proves A, and B proves B. So kind of not terribly surprising that that worked out. Let's try cut. So what's the statement of cut going to be in the system? Let's actually think about that for a minute. Well, it's going to start with this. But
some other omega double prime. So we're trying to cut out
let's call them,
a chunk of the context.
right, so let's call it omega left and omega right. And what do I have in the middle?
A.
Proves C. Then omega left, omega right proves C. All right, so let's just check the principal case to make sure we're not crazy. If I've got D1 and D2, which is omega 1 proves A, and omega 2 proves B, and omega 1, omega 2 proves A conjoined with B. And then over here I have omega left A AB, omega right proves C. Then all right. And what I have to show is that omega left, this context, which is omega 1, omega 2, omega right, proves C. Is that right? So give me a smaller cut.
D1 against E1.
All right, so if I cut D1 against E1, then I'm going to get delta 1 proves A, delta left, oh, sorry, delta, omega left, A, B, omega right proves C. And this is going to give me, didn't quite leave myself enough room, omega left, omega 1, B, omega right proves C. Did I get that right? So now what do I do? Right, I cut against B. Omega 2 proves B, D2. And so this is a cut with the formula B, and this is a cut with the formula A. And so again, I'm cutting the output of a cut. Why is this okay here? The principal formula got smaller. Okay, so we haven't fully worked out the cut admissibility proof, but in this case, we at least have some notion that we might be sane. And so what this is, the interpretation that this is giving us of our connective is that this is an A followed by a B. And so the way I decompose that is to make an A immediately followed by a B. Okay, so a quick one, I won't even bother doing the cut.
Question about,
Yes?
so you reversed the proof already, but in the proof of identity expansion for the persistent logic for A
Yeah,
and B, is then the conjunction is both positive and negative, right? Because we can also
Right.
use the other elimination.
I made it very strange to illustrate a point. And in fact, it is true that conjunction in persistent logic is a little bit confused as to whether it's positive or negative. And you can define that in persistent logic, you can interderive them. So that's a very good point.
What is it actually? Is it considered positive or negative?
Pick one or both.
Okay.
In fact, if you take, so we've done, so Christina's question is that it looked like the rules that I wrote down for in the persistent system were both, the conjunction was sort of positive and negative. And that's a very good observation. Conjunction in linear logic, whether we duplicate the resources or not, forces us to decide whether conjunction is positive or negative. If you take, and so we could sort of take every connective one by one and say, you are positive, you are negative, you are positive, you are negative. In persistent logic, when we just formalize persistent logic, if you look at conjunction and you're like, well, there are two of you. There's the positive one and then there's the negative one. And you mean the same thing from the perspective of provability, but you mean different things for the structure of proofs. And so that's, I think Dale Miller and Chuck Lang were the first people to sort of write that out carefully. But I think even Gerard noticed it in the original paper on linear logic, that we've split conjunction into two. Okay, and so yeah, once we deal with substructural logics, we can't get away with splitting conjunction into two. We can easily see, just when you're talking about what we can prove, not just how the proofs are shaped, that there are two different conjunctions. All right, really quick. So the rule for 1 is that if I have nothing in my context, I can prove 1. And the left rule for 1 is that it goes away. So this looks much like what we've already been dealing with. Okay, I'm going to have to... this is a little wider than I'd anticipated. So I'm going to keep writing these rules over here. Somebody propose for me an implication.
A implies B implies A implies A.
Someone proposed to me a rule for implication.
Move the A into the end of the context.
Which end?
It's a good question.
The lecture is yours. Which end will it be? That's correct. Pick one. Right side or left side? Right side. Chris?
Shady side.
Okay, so you have picked the right side. That means that I will draw the arrow thusly. And this is what's called, oh, no, crazy. What am I doing? That was insane. No one look at the board. Okay, now you can look at the whiteboard again. I've moved the A to the right side of the context. All right. Now, and if you get this wrong, you will be exactly like me approximately 50% of the time I have written down the system before checking the principal cut. Give me a left rule for implication, for this implication.
Well, I'm going to say it's the same as the one from linear logic. Yeah.
All right, so I think the one from linear logic would have me do this, right? Delta prime proves A. Is that the one from linear logic? Okay, so let's try that. Left.
Oh.
And let's call this A. And let's call this omega right.
So omega left proves A. And
Omega left, B, omega right proves C.
but B comma omega right.
B comma omega right.
Yeah.
All right. So this is a completely plausible rule for right-ordered implication. Let's see if it checks out. There are two things we can check. Which one would you like us to check, identity or cut? Let's do identity. So A writes B, A writes B. So there's really only one rule I can do here. It's the right rule, right? So the right rule puts things on the right-hand side. All right, what now? Yep, okay, so you guess the way that I do half of the time, which is, all right, no harm, no foul. Let's just flip it around. A right implies B, omega A. All right, now we can apply the left rule. A, B, B, where omega A was equal to A, omega left was equal to omega right, which was empty. All right. So let's check cut as well, because now we know it's possible to get these things wrong. Thank you, by the way. I was badly hoping that we'd get the wrong one first. Because I swear I've gotten, like, if I am writing out, there are two ways I remember which way this works. One of them is I have an internet connection and I look up one of the papers I've already written that has ordered logic in it. And the other way I do it is I write it down wrong. I try to prove, actually I usually try to prove cut, but trying to prove identity I now realize is a much easier way to realize that I was wrong and then do it right. All right, so let's prove A, B, and we've just got delta A proves B. And now we have a left rule, which is that A, B, omega A, omega right proves C. Okay. And now I've got omega A proves A, and that's E1. And I've got omega left, B, omega right proves C, and that's E2. Okay, so how do we, so the thing that we want to prove, right, is delta left, sorry, omega left, omega, omega A, omega right proves C. Any suggestions on how we start? All right, that looks good. So if we take E1, A proves A, and D2, which is that omega A proves B. Frank can draw dashed lines way better than I can. Let me try that again. Well, he can draw them faster than me then. A proves B. Okay, so now we have a smaller formula, and we can cut this against E2. Omega left, B, omega right proves C. And then we have the thing that we need, which is omega left, omega, omega A, omega right proves C. Okay. So somebody give me another rule for implication.
Right or left?
Well, we've already done right. So why don't we try?
Right or left rule for the other. Okay, whatever.
Yeah, give me the right rule.
Same thing except A and omega transposed on top.
Yep. So this one is called this is the right rule. Yeah, this is why I was confused. This is the right rule for left ordered implication. And the left rule for left ordered implication is going to put omega A to the left of the proposition. So omega left, omega A left implies B, omega right proves C. If omega A proves A, and omega left, B, omega right, proves C. OK, I won't go through the cut elimination proof of that because it's just the transposed version of this one. So now we have sort of spread awkwardly around the, across the whiteboard, and my apologies. But now we have some rules for ordered logic, also called ordered linear logic. And that's an interesting statement that it's called ordered linear logic. So you saw in the midterm that it's possible to use the connectives of linear logic to define affine logic and to define relevant logic. I haven't really stated this, but in fact it's not possible to use propositional ordered logic to simulate, or it's not possible to use propositional linear logic to simulate propositional ordered logic, because ordered logic is sort of more strict, and so you can only use these exponentials to describe less strict variables. However, what most presentations of ordered linear logic have, are some exponentials. In fact, it's really the exponentials that make these logics interesting. So we want an analog bang A to the system that we've been dealing with so far. And that's going to be a modality that allows us to treat a proposition as unrestricted, which means it can go anywhere and we can use it any number of times. After we do that, we're also going to want to define a modality. Forgive me for calling this GNAB, but I've not heard a better name for it. So a modality GNAB-A that's, so this is persistent. I guess we've also used unrestricted. And this is linear. So we want to define a modality that lets us use this linearly. As before, this means that we're going to have to change our formulation sort of throughout. Let's first add the persistent bit. So that means that we're going to need to add a context gamma everywhere that acts much like the one we already have. And I'm going to leave room because I'm going to put the linear one in the middle. But we're going to, and our sequence now looks like this. And so what should we need an analog to the copy rule that we had before, because that's the thing that really hooks in the persistent resources. So what do we want the copy rule to look like? So I've got this, and let me, to be careful, write A is in gamma. So what do we want to say here?
You want to be able to put it anywhere, so.
Right. And then I'm just going to stick this in the middle. OK, so this is copy. And now let's write out the rules for the exponential. So the easier thing to describe is how do I use. So I've got somewhere in my context a bang A. Well, whoa, that was exciting. Then this is just as before. I'm going to add that to the persistent context. So now that now I can copy it in any number of times. So this is being left. What's being right? Right, haven't written the linear, but if I can prove it with an empty ordered context, so just like the way I wrote 1, then I can prove Bangay. So to get the to add linearity in there, I'm going to add a second context, or third context, sorry, the linear one. And so the linear one, well, that just basically gets placed everywhere. But we need a new, and here, like Arbab said, I also need the linear context to be empty. So we need a new copy rule, or something that's kind of like the copy rule. And the way that this works is that we say if I have somewhere in my mobile resources, because linear resources from the perspective of order logic, they're mobile, they can move around. If I've got among my linear resources 1A, so just to emphasize that, well, this is a multiset, but I'm really putting it in the middle. One of the problems that shows up when you deal with ordered presentations is that you have to start working between this, well, some of these contexts are lists, some of these contexts are multisets. I'll try to stick with the notation that lets everything be a list, because that's a little bit more consistent. So if I've got somewhere in my context, my linear context in A, I can put that at any point in my ordered context, just like I could before, except that now it goes away and it's no longer in my linear context. Delta 1, delta 2, left, A, omega right, prove C. And the right rule for mobility.
What do you call that rule?
Hmm?
What do you call that rule?
The right rule for mobility?
The one you just wrote.
Oh, place.
Oddly, that was what I came up with.
Say what?
Oddly, that was what I just.
Yeah, that's something that I think goes back to like, so Frank and one of his students about, I guess, some number of years ago, Jeff Polikow, wrote a lot about ordered logic, or ordered linear logic. They were kind of the people that developed the system. So the place was the thing that they usually use, because I'm taking. Okay, but the reason this is so copy is I've got this bundle of stuff that I can use any number of times, and I want to copy it in to the ordered context where work can happen. And now I've got sort of a bag of stuff that I have not committed to putting anywhere, and I am placing it at a particular place in the ordered context, looking from bottom up. And from this point onward, it will be there. So place is the typical name for this. The right rule does require that the ordered context be empty, because I can't depend, if I want something to sort of agnostically be anywhere in the context, there can't be ordered stuff around. But there can be linear things that are floating around. So this is A, Okay. And now I need to find a place to put the last rule. I'll put it here. Oh, right, sorry. I was already skipping ahead to the left rule. And so the left rule is going to be the thing that I was just trying to write down, sorry Bob, which is that if I have somewhere in my linear context, somewhere in my ordered context, a mobile A, then I can just move that into the bag of resources that get to go anywhere. Yes?
So that means that the rules only take place in the ordered context, right?
Yes.
They never.
Which is analogous to linear logic, where the rules only take place in the... Right. So the connectives that we've considered are A, B, A, right implies B, bang A, and nab A. Those are going to be all the rules that I'm going to write out, but what are some other ones we could have defined? Oh, yeah, 1. Okay, that's good. Thanks. Right. So we can get something that looks very much like the additive disjunction from linear logic. Fuse. Okay, right. So there's also, in a lot of presentations, which is just backwards A fuse B. Because you can get from one to the other, you can get from one rule to the other by just sort of rewriting the formula. That's a little bit, I think it's not necessarily a clear story whether this is a proper connective, because you can kind of define these in terms of each other. But you're right, that is a thing that we can give rules for that makes sense. One more? So you can have additive conjunction just like before. So from the perspective of saying, one interpretation, and I'll give an example of this in just a second. One interpretation of this kind of sequent is that, and in fact it's the one from the original presentation of ordered logic by Lambic, who was a linguist. And so he wanted to use this logic to describe the structure of sentences. The interpretation that he gave was that this is a sentence, like, Mary saw Bob with binoculars. And then this is the part of speech. The conclusion is the part of speech that sentence matches. So this would be, Mary saw Bob with binoculars is a sentence. Let's actually give a... I'll erase the outline because I don't want to lose this just yet. And it kind of reminds me of reading Rainbow. I like it. Say what?
Sorry, I have a question.
Yeah. Go ahead.
Okay. So here we either. Sorry, I can't focus.
It's fine. You're forgiven, whoever you are, but you might want to turn your cell phone off, wherever that is. Okay.
Yeah, okay. So in the
Wait.
It sounds like it is kind of a
Oh, wow. I don't know. If it's me, that's going to be hilarious, but I don't think I have any technology on me that could make that sound.
So my question was, we have these two implications, the one which requires A to be proven immediately before.
To be to the left and one to the right, yep.
But what if we want to have an elimination rule where A allows, where we can prove A later?
Where we can prove a,
Where the delta A,
it can have a non-local,
yeah,
yeah,
where the omega A would be on the right hand side.
so the way that this is usually put together, oh, is someone trying to call us? Yes. Okay. No? All right. So for the interpretation of ordered logic that we sort of started with, these things tend not to work out, I think is the best answer I have. That's not to say that they can't be worked out or that there's not a formulation for which they work out.
Yeah, I can
But,
see that we
yeah.
wouldn't be able to find like the corresponding right rule.
Yeah, that's generally the idea.
I was just wondering why that is.
Yeah, I mean,
What's the question?
so the question, sorry, I should have repeated it, was both of these right rules require the sort of subcontext that's used to prove the premise, omega A or omega A, to be right next to the thing in the proposition that we're dealing with. So is there a sort of non-local implication? And I frankly don't know the and for the formulation of ordered logic as it's usually defined, there tend not to be a formulation that.
I mean, you can prove like an implication where the first.
Oh, hi! You're in Portugal. We have changed so I sent an email saying that we weren't getting that we weren't going to be able to manage the feed today. Also, we've switched in daylight savings time in the United States, so you're going to actually need to connect an hour earlier in the future. As long as this feed stays up, that's cool, but if the feed goes down, then you'll need to reconnect over the live stream, which you probably want to do anyway because you missed the first hour of lecture. So sorry about that. But yeah, daylight savings time changed the time of our class relative to yours. I think that Europe goes to daylight savings time in about a month. And so at that point, we'll be synchronized again. But there's a bit of time skew. Oh, next week. OK, so this is only a problem for this lecture and the next one. OK.
Prove like map A, some arrows here.
Right. So one of the ways is you could make this as a compound connective. You could have like gnab A, arrow B, and then that would work just fine. It's a good question, and it's one that might be worth exploring in projects later in the course. But for other formulations of implication, you just can't make cut and identity work out correct. So I wanted to give a little example, which is just of the. So let's have gamma is equal to the following. That Alice, which everything I'm writing down is an atomic proposition. Alice is a noun phrase. And saw, or ran, is a verb phrase. And a noun phrase followed by a verb phrase is a sentence.
Back to writing it like that, you mean that left implication is our internalization of entailment?
I have decided to make left implication our internalization of entailment.
Is
Yeah.
there a reason that we picked left, or is it just like pick one and stick with it?
Because this is in the persistent context, no, it really doesn't make a difference. Because the way that we're going to use all of these things is copying them in. And what we're going to do is just copy them in to the left, or to the right rather than to the left. Right. So yeah, I made a bit of an arbitrary decision, and you're right to ask me why. It doesn't turn out to matter for the purpose of the example that I'm playing out. All right, so now I want to show with this that Alice ran. So I'm just going to ignore the linear context for this example. Alice ran is a sentence. So how should I start? There are actually two options. They both involve the copy rule, but you can pick. Actually, there are more than two options. But
Copy rule for
so I can pick any of the three of these and copy them into the context. I'll go ahead and pick the first one. So I'm going to want to put this in the middle so that I can pick up the Alice, which will then be on the left. So this is going to be gamma Alice,
Your ordered context, is that Alice dot or Alice comma?
comma, ran, yeah. So this is my sentence, and this is my string of tokens, and this is the thing that I want to parse this string of tokens as a sentence. This is a constituent grammar, I think, if you're a natural language processing a natural language person. And so I'm going to copy into the right of this Alice. Right implies noun phrase. Ran. Prove sentence. And Alice is an initial rule. And then gamma noun phrase ran. Did I get that right? Oops. So now I'm going to do the copy rule again. Noun phrase ran. This time I'm going to copy in this one. Ran goes to verb phrase is a sentence. Ran proves ran. And noun phrase, verb phrase is a sentence. Now I'm going to copy in this one. Noun phrase, verb phrase. Noun phrase concat with a verb phrase gives me a sentence. And I'm now going to prove gamma noun phrase, verb phrase, proves the subgoal. Noun phrase times verb phrase. And I have sentence proves sentence. I can finish this one with the implication, or with the conjunction right rule, because I take the noun phrase to prove noun phrase, and I take the verb phrase to prove verb phrase. And I've shown that Alice ran is a sentence. That was easy. But there were a lot of other ways that I could have formulated this, a lot of different orders I could have done the copy in. So we've got this problem that there's a lot of non-determinism if we want to talk about this parsing. So how do we reduce non-determinism in a sequence calculus? Hey! The notation that Frank has used for focusing is simple enough to just annotate rules with. What do we want to put in focus for conjunction? The right rule, because this is invertible. For 1, we want 1 is just the unit of conjunction, so we want that to look like this. Now, what about implication? Way over here. Left. And not this, left. Okay? What happens to our, oh, right, and so now we also need to deal with two different initial rules for positives. So this is, if I'm right focused on a positive atom, I can succeed. And if I'm left focused on a negative atom, I can succeed only if that's the thing that I'm ultimately trying to prove. We need rules for blur and focus, for actually going into and out of focus. So this is going to be if I'm right focused on a negative proposition. And the negative propositions are this one and that one. Everything else is a positive proposition, though these are, just as before, have positive to the left of the arrow, because we stay in focus when we work on the left. And so this is going to be a blur. Delta omega proves A minus. And if we are not focused on anything, and if we want a fully focused system, we need the extra restriction on a focus rule that focus. Well, so what are the extra restrictions that we need if we want this to be a fully focused system as opposed to a weak focused system?
You want delta and omega to only include negative propositions and positive values.
It's actually just omega. But yeah, basic, that's so only A minus and P plus. Because when the mobile context has the same behavior of the context that we had before, it doesn't matter, this is the invertible rule in this case, and it doesn't matter what A is, we're going to put it in the context. And so any proposition may go there. And as soon as we put it there, we can't decompose it any further. Similarly for if I've got a left proposition, if I'm left focused, and I can only be left focused in my ordered context, left A plus omega right C if gamma delta omega left A plus omega right proves C. And we've got another rule that just lets us, and I'm only going to write out, this is omega left A minus omega right proves C if omega left focus on A minus omega right proves C. Okay, that was kind of badly written, but those are the idea of the focus rules. So we just have to deal with the focusing behavior of the exponentials, and we've got the whole focusing system down. For mobility, what do I focus? What is the focusing behavior of this one? I'm going to lose the focus, but where am I going to be focused at all? On the right. Okay, yep. And this is actually an invertible rule. So, wait, no. That's actually an invertible rule. Do I need to do anything to place? Yep. So if I place something in the focus system, I have to immediately focus on it. just like if I copy something in the linear system, I have to immediately focus on it. And again, I am focused on A, and then I have that. All right, so I think, let me just, nope. That doesn't turn it off. Okay. So this is the focus system. Let me just write out and let's see, is there a way to, okay, fine. There. So I think I can, I'm trying to think what I want to do with the last 3 minutes. I was going to do a description of how the substructural operational semantics that we can do, that we've dealt with in the past can be described using ordered logic. But I think I want to do just a slightly simpler example because something that I can get across meaningfully in 2 minutes. So let's look at those two rules that we were dealing with before, or like the noun phrase times verb phrase goes to sentence. And let's figure out what's the derived rule, what's the derived behavior in the case that this is a that all of these atoms are positive. So that's the game that I want to play through. So if I've say that I've got this in my context. So what happens first is that I'm going to copy, which is going to give me somewhere in my context a focus on noun phrase, verb phrase, sentence. Okay. So the only rule that I can pick at this point is that I have to right focus on noun phrase times verb phrase. And this means that I have to divide my context into two parts. The left part used to prove noun phrase, and the right part used to prove verb phrase. And because this is a positive atom, that means that this context must be exactly noun phrase, and this one, or verb phrase, and this one must be exactly noun phrase. So I know that this has the structure noun phrase, verb phrase. This is that, and so now I have a sentence here that I'm focused on the left, but that's a positive atom that I'm left focused on, so that's just going to get placed in the context. Okay? So now if I fill out what the rest of this looks like, there's some arbitrary context to the left and to the right. I've got a gamma, gamma, omega left, omega right, omega right. But here I need noun phrase, verb phrase, and this is omega left, and this is gamma. Verb phrase. Thank you. And this is a C. And this is omega left, noun phrase, verb phrase, omega right proves C. So the derived rule we get from focusing where these are all positive atoms is that we go from a context where I just have a noun phrase and a verb phrase to a context where those two have been replaced by a sentence. That's basically the picture that I drew when I did this by hand. I was working as if these were all positive atoms. Now if I want to give the derived rule where, now if I want to give the derived rule where everything is a negative atomic proposition, I'm going to start off with noun phrase, verb phrase proves S. I'm going to need to prove noun phrase, verb phrase. This means I split the context and I prove noun phrase. And I prove verb phrase. But if these are negative atomic propositions, then I have to blur because I have a right focus on a negative proposition. And I have to blur again here. So this can be any sequent for which I can prove noun phrase, and this can be anything for which I can prove a verb phrase. Omega 1, omega 2, omega 1, omega 2 proves noun phrase, verb phrase. And then I stay left focused on S here. Now S is a negative atomic proposition, which means that I can only succeed if the thing that I was trying to prove was S. And there's nothing else in the ordered context. Which means that here, omega left has to be empty and omega right has to be empty. So the structure of this has to be omega 1, omega 2, noun phrase, verb phrase goes to S, proves S. And we have a very differently structured rule where it says that if we can prove that part of our the first part of our sentence parses as a noun phrase, and we can prove that the second part of our sentence parses as a verb phrase, then we can prove that the whole sentence parses as a sentence. And so we've played out this game before with the fact that positive and negative atoms lead to radically different search behaviors. Here what we're seeing is the way in which this leads to different, essentially, parsing algorithms, given how we describe the positive and negative atoms in the grammar.
I think you used the wrong arrow.
Yep, I did. Thank you. Oh, also, to kind of answer your question, I think when I'm writing out these examples, it looks a little bit nicer to have the part of the arrow that is closer to the context be the thing. So when all things are considered, I actually think the right-ordered implication looks better. This is a new decision, the first paper that Frank and I wrote on using these sort of derived rules of inference to describe operational semantics, used right-ordered implication instead of left-ordered implication. Okay. That's, I think, wraps it up for today. Thank you very much for your attention.